which I realize is a little bit of a mouthful, but you'll see some pictures and we'll kind of walk through it. I'll go through some of the terms right now. So spectral estimation is trying to get see how data varies over time, like a power spectral density estimate, something like that. Robust means that if your data has outliers or is corrupted, you're still getting a good estimate. Blind means that a lot of this has to do with signal detection, so trying to figure out like which signals are in the electromagnetic spectrum and trying to find them. Blind means you're not really assuming much about those signals. Impulsive noise is noise that has like a lot of impulsive spikes in that. It could be caused, like a traditional example would be like a lightning strike hitting a power line would cause a lot of impulsive noise, but there are many sources. So I'm going to talk about some of the motivations, which are spectral estimation, robust estimation, and signal detection. Those are kind of like the main three areas that I'm merging together. I'll talk about standard spectral estimation techniques and what I've done. So the Welch and the multi-taper method are spectral estimation methods that exist already, and I've modified those and to make my own custom version and to increase their robustness. And then I'll kind of give you some pictures and some descriptions of what impulsive noise is and the model that I'm using. I'm using a statistical model to generate synthetic noise data. It's called Middleton Class A model. And then I'll show the results. So here's the definition for spectral estimation. From a finite record of stationary data sequence, estimate how the total power is distributed over frequency. And there are many different types of spectral estimation depending on what you're doing. And this presentation, or my thesis, was concerned with non-parametric spectral estimation, which essentially amounts to just trying to find a power spectral density estimate. And I'll show you what that looks like later if you're not familiar at all with what that is. And then you got blind versus feature-based signal detection. Again, feature-based would be, say you're trying to find a signal in the air. If you know things like where it lies in frequency, its bandwidth, its modulation type, all that kind of stuff, and you're utilizing those features, that would be feature-based detection. I'm not utilizing any of those features. And then there are some methods that already fit as non-parametric and blind, and I'll be talking mainly about the Welch and the multi-taper. But I'll start off with the periodogram. And then robust estimation, again, that goal is accurately estimate features such as location or scale of data that contains outliers. When I say estimate a feature, I mean, let's say you have any set of data and you want one number to characterize the size of that data. You might take a mean or a median or a mode or any. Those are all ways to estimate where the data is located. You could just take the ages of everyone in this room, take a mean, and that would estimate the age of this room. And then scale is the same thing, but like how the data spreads. So you might be familiar with the variance or something like that. And then there are different applications for robust estimation that kind of motivated this work, like power line communications and cognitive radio. So when you kind of combine all these things together, you have spectral estimation, the non-parametric spectral estimation, the bottom left, and then if you tried to perform that task when you have impulsive noise from the top, you're adding in your robust estimation element. And then if your goal is signal detection, that's kind of the last piece. And all of those three pieces come together, and it motivates this central question, which is, can the signal detection capabilities of the Welch method, that's a spectral estimation method I'll talk about, be made more robust for non-Gaussian noise scenarios, and if so, which scenarios? And non-Gaussian noise just means noise that isn't characterized by the Gaussian distribution. And there, it's a very broad set of noise distributions, but specifically what you'll see is that I can increase the robustness, but only for impulsive noise, not for non-Gaussian noise in general. So let's talk about spectral estimation a little bit. I'm not going to go through the details, but if that is one form of the equation for power spectral density, xn would be data samples, f is frequency, phi is your power spectral density, and yeah. But there are problems applying that equation in practice. So let's say we had a signal xn and we wanted to apply that equation to find the power spectral density. There's a problem because it has a limit that goes to infinity, so we need a signal of infinite length. That usually doesn't work out well. And there's an expectation operator, which means we only have one realization oftentimes, so we can't use that expectation operator. And also f is a continuous variable. So and that doesn't work well for computers. So if we use one realization and we make it finite, and we change f to k over n, we get this, which is it's called the periodogram. So first picture. So the left one, on the left, you have just a plot of a signal. You could think of this as like putting an antenna in the air and just reading the radio waves or whatever. But it's synthetic. And what that signal is Gaussian noise, which is a really common type of noise, and a QPSK signal. It's just a type of communication signal. And if we compute this this periodogram right here, the hat means it's an estimate. We compute that, we get our noise floor right here. And then our signal pops up right here, and you can see the energy of that signal. And it's located in the center. For all of these, I've just located the signal in the center, but it could be elsewhere. But you can see it's really noisy. It's not like a very clear picture. So you might think that, okay, what if we use more than 256 samples? Could we do something better? And we would get this. We increase to a little over 8,000, use more samples. And the picture is a little more clear, but you can still see there's a lot of variance. So that's when Peter Welch stepped in, and he took that equation, which was on the previous page. And rather than just using this equation and computing it on all of x of n right here, he chopped it up into pieces and computed the periodogram for each little piece right here, each nth piece. And then he averages them together. And you get this. So now you can see far less variance. When I say variance, I mean it's pretty flat here. And you can see the signal pop up. And then less variance. So this would be what you call your noise floor. That's the AWG noise, and then the QPSK signal. And this is good because you want to be able to see, if you can see your signal clearly, then you can detect it easily. You can just run like a peak finding algorithm or something and detect it. So that's kind of like the main thrust, is can we get a good picture of our signal? So I took Welch's method and I modified it a little bit, as I said previously. For those of you familiar with robust estimation, the mean is not a robust estimator, so it's heavily affected by outliers, and this right here, sum divided by m, is a mean. So I decided to try to swap that out with different estimators. I used a median. So median, if you have a set of data, I just threw up some data there. You order it and pick the middle. That's a median. It's far more robust. And then a Hoover modified, which is just another very popular robust estimator. So I tried both of those. So I took this piece right here and I replaced it with the median. And the other thing that I did was I took something called, so here's our picture again, where we compute the Welch method computes the periodograms for each piece here, all the way there, and then averages them together. And it does that bin-wise, so for each, it lines up the frequency bins and averages those together. So I took the multi-taper method, which is another method for spectral estimation, and I inserted it, I replaced the periodogram for this piece, and I inserted the multi-taper method in there. And then I again swapped out the mean piece, that sum, and divide by m with standard robust methods. And by the way, you stop me, I meant to say, but stop me whenever you want to ask questions. Okay, so let's talk about some noise. So here are some realizations of noise. I just took the noise model and generated a bunch of noise samples. And I'm showing the complex envelope, which is like the magnitude, that's just like the magnitude of the noise. And it's 10,000 samples across. And this is pretty close to Gaussian noise. And you can see that it's pretty flat. The amplitude's pretty consistent. But if we get more impulsive, then you get these spikes, these noise spikes here. And then this is something in between where you have smaller spikes. So I'm kind of trying to show that you can generate different types of noise. Some is more impulsive and some is less impulsive. And then you can, and this is a little hard to see, but you can also make your noise more or less Gaussian. So if you've seen this, again, looks very much like Gaussian, and this, it's not impulsive, because you can say there aren't really impulsive spikes like you do here, but it's not quite as consistent. Or it's not as flat. So if I go back to these pictures are all numbered, 1, 2, 3, 4. And those correspond to 1, 2, 3, 4. So I'm not going to go through the details of the Middleton class A noise model, but it is a probabilistic model. Here it's the PDF of its envelope and the PDF of its phase, and some parameters that control the shape of the noise. So I'm just I do need to talk about the parameters and what they do. So if you select a sigma squared, an A, and a gamma, which is the total power, overlap index, and Gaussian factor, and once you select those, you have then, for the Middleton class A noise model, you'll get a noise characterized by these parameters. And what the A, this is just the total power of the noise. The A controls how impulsive the noise is. So let's kind of look at that. Here, these are all just realizations of noise with different parameters. And here A is decreasing more impulsive. So this is pretty flat, but here you have the flat piece down here, and then a lot of impulses. And then the Gaussian factor, gamma, controls the ratio of Gaussian noise to non-Gaussian noise, and that goes in this direction. So the further we go that way, the more non-Gaussian it gets. So my goal, if we return to the whole idea, the reason I'm showing all this is I wanted to know, can I increase the robustness of detection for different types of non-Gaussian noise scenarios? So I've just generated a lot of different noise scenarios. The ones on the top are really impulsive, the ones down below aren't as impulsive, and then they differ left to right as well. So I'm going to test my method in all of these scenarios and see how it works. And as I've already said, you'll see that my method doesn't outperform the standard method in these scenarios because they're not impulsive. But in these upper ones, you do get some performance increase. All right. So the first thing I wanted to do when I was trying to figure out where to, like, what parameters to choose for my noise model is I wanted to search the literature to see what people are using. So I found papers where people were using the Middleton Class A noise model, and they had values for what they were using, and I plotted them here. So one axis is gamma and one is A. And the box is the part of these scenarios, the edge of here, and then I've picked locations in between. So I'm trying to be as comprehensive as possible and kind of look at all the scenarios people consider to figure out. Yes?
I have a question about the graph.
Yep.
The max time.
Mm-hmm.
Okay, so for the third, like at the very top, yeah, why is there only like one impulsive jump?
Yeah, one impulsive jump. Yeah, it's because one of the way when I say this A is overlap index controls the impulsiveness, what I mean is that as you go up, you get fewer spikes, but larger spikes. So, and I probably should have pointed this out, but these axes double. This is 5, 10, 20, 40, 60. So if this spike looks just as big as that one, this one's twice as big. And same here. So these might look just as big as that, but these are twice as big. So you can see you're getting fewer, but they're getting bigger. And that's what I would call more impulsive. Does that make sense?
Mm-hmm.
Great question. Other question?
Did you look and see what the Gaussian factor actually did to the distribution of noise compared to that? Just out of curiosity.
Yeah, so
what does it change about that?
yeah, that's a good question. So the way, a good way to think about it, you could look at the PDFs maybe and kind of compare like the PDF and see how that changes. The way I would think of it is, see how you got this like minimum band of noise here, and then you have times in which it's higher than that, okay, more peaky than that, larger amplitude. If you were to take the noise realization at just this level, that would be the Gaussian noise, okay, because Gaussian noise again is flat. And then all the additional power that comes from the spikier pieces, that's your non-Gaussian. Okay, does that make sense?
Yeah.
So again, you got your band of Gaussian noise and then the spikes that increase on top of that. And so your gamma is actually the ratio of that. So, and yeah, you can kind of see it in here in the PDF, but if I don't know how many PDFs you've looked at, but if you cover up this part and just look at this, I don't know if you can see that. That's the PDF of a Rayleigh random variable, which characterizes the envelope of Gaussian noise. And so it really ends up being a weighted sum of Rayleigh random variables that increase in magnitude. And the smallest one is the Gaussian part. So, any other questions? Okay, we'll go. Okay, so some parameters I'm using for my simulations. These ones are static, the top ones, the samples per symbol, and the pulse shape, root raised cosine, and the overlap. So, you know how I said, I have that picture of the segments that the multiple segments, those overlap by a certain percentage, and 50% is really common. So none of those, I'm not looking into how those change the results. The parameters I'm concerned about are A and gamma because they affect the shape of the noise. I want to know when this is relevant. I want to know if the modulation of the signal affects how well I can detect it. I want to know if the segment length helps, like a shorter or longer segment length helps increase my detection capability. And I also, you can choose how many segments you want to use, and I vary that a little bit as well. So we're going to go through an example. Oh yeah, so this is the simulation conditions. So what I did is, for each scenario, for the noise in each scenario, I basically took that and I added it onto a QPSK signal. So then I got my noise and my signal, and then I tried to find the signal in the noise, for example, and gauge its performance. I should note that adjusting gamma and A does not change the total power of the noise. So you know, remember how there were three parameters, sigma squared, gamma, and A? Sigma squared is how you choose the power of the noise. A and gamma don't change it. So the power of all of those is the same, is equal. So if you define S and R as signal-noise ratio as the power of your signal divided by the power of your Gaussian noise plus your non-Gaussian noise, I'm keeping that constant. Or if you think your energy per bit of your signal divided by the noise power spectral density, I'm keeping that constant at 3 decibels. So I'm going to walk you through slowly what happens in scenarios 1, 2, and 3 on the next slide. Here. So I've taken 1, 2, and 3, I've blown them up a bit. You can see we're going more impulsive that direction and also more non-Gaussian. But again, the thing that matters is whether you're impulsive or not. That's what we'll see. 10,000 samples. I'm using QPSK and a segment length of 256. So each periodogram is 256 samples. All right, so let's try to find, we'll apply that noise to our QPSK signal and try to find it. So you can see that the traditional method is in blue, and here are my robust modified versions. You can see that all of them, the signal pops up nicely right here, and so they all work relatively equivalently. And I should know that I define effective SNR by the distance from here to here. So when you want to say how easily can I detect a signal, you think how high above the noise floor does the signal pop up. That's what I call effective SNR. As we get more impulsive, these axes change. The blue, the traditional actually remains the same, but we're getting a larger effective SNR for the robust methods. Because what ends up happening, just hand wavy, is you break this up into different segments, and the segments that have the really bad impulses in it get ignored by the robust methods. And they don't get ignored with the traditional method. And because you can kind of filter them out, you can think of it like that, you end up getting a good picture of your signal because you're only looking at the segments that don't contain the impulsive noise. And then, yeah, the top one's even better. But there's a problem with this. We have 500 segments, which is a lot. If you look at the literature, people probably use like 10. So I wanted to use 500 because I thought it would kind of give like a good average performance. But if you think about it, like if you tried to find a signal in any part of this, you'd be able to find it unless you're looking at this part right here. Saying that if you try to find a signal and you just use samples from here to here, you'd be good. But if you overlap with this, you wouldn't be good. So instead what I did is I reduced the number of segments to 10, so I'm looking at shorter pieces. And then I made a histogram of the effective SNR. So we'll go through this bottom one. So again, effective SNR is the distance from here to here. So that would be like 6 or 7. And this is a histogram, and the bins go from 1 to 3, 3 to 5, 5 to 7, 7 to 9. So what you can see is the effective SNR is very consistently between like 6 and 8, which is about the size, which makes sense. If you go up here, you can see for the robust methods, the red and the orange or yellow, the effective SNR is always above 10, right? It's always this large. But sometimes the blue one, the traditional method, has a really small effective SNR. And even up here, sometimes, again, most of the time the blue one works, but if you're ever looking at a segment that contains the impulse, it won't. Does that make sense? Questions?
Do your left plots contain the signal that you're estimating?
These?
Yes.
No, these are just noise. Yeah, I'm just trying to show the way the noise is characterized. Alright, so I kind of stepped through 3 scenarios, and now we're going to look at it on that big 5x5 grid, but again, most of the, yes?
So the effective SNR of the traditional Welch method in the top right,
Yeah.
is it like 9 dB?
Yeah, so there's some information lost in the way the binning is done, because everything above 9 gets binned at 10.
Okay. Like if you look at the spectrum, it doesn't appear to
Here?
be. Yeah.
Yeah, that's because we have 500 segments, so we're looking at like it would be a lot of noise, which means we're going to have some segments that are heavily biased by like a big impulse, but most segments are good. And when you end up adding those together, you're going to get something around like 5. But again, that's like way too many segments to use, and it's not realistic. And what would happen realistically is you would either land like in this region, in which case you would see this signal easily, and so that's this. Or you would have you would land in this region, but because you're looking at much more data, it would totally destroy your estimate completely. And you'd get there. Does that make sense? Yeah. Okay. Any other questions? Okay, so again, looking 500 segments again, just like in the second row of the previous one. And the good thing is all of the bottom two rows and here all perform similarly, and you start getting performance increase in really the top left corner and some differentiation here. But same idea, this is 500 segments, so we want to reduce that to 10 and look at the histograms because that gives us a little more information. But you'll see that because the bottom rows are the non-impulsive noise, the histograms are again going to perform very consistently, and we'll see differences up there. And that's what we see. And just recall, the way this has been looks confusing potentially. It's not truly bimodal. It's just that there's variance in the estimate, and so sometimes it gets spin from 5 to 7, sometimes it gets spin from 7 to 9. Anyway. So these all perform similarly, so not too much of interest, but again, we have the differentiation here, a little bit here, and a little bit here, for the same reasons. Any questions? Okay. Here, really similar story. That was all talking about the Welch and the modification to Welch. I mentioned previously that I used the multi-taper method, and I inserted that for the periodogram and did some stuff with it, and I called that the multi-taper Welch, and then my median version of that, whatnot. And without getting into the really nitty-gritty, essentially you see the same thing. There's a totally different conversation you would want to have as to why you would want to use the multi-taper. And that kind of amounts to a variance versus computational effort trade-off. But as far, if you just want to think about it in terms of robustness, you kind of get the same thing. So, all right, so I did this again, but with the previous example, I told you that the total noise power in all the plots was the same, which meant that when I applied that to a QPSK signal, the SNR was the same for every plot. But that doesn't, it might make sense to think about it in that way, depending on who you are in your application, but it also might make, I think this way makes a little more sense. What I'm doing here is you have your underlying Gaussian noise power, and I'm holding that constant. And then the non-Gaussian noise power changes. And so what your result is, so you have this idea, you have your signal, the ratio of your signal power to your Gaussian noise power is constant. But that's not your SNR, because we've ignored the non-Gaussian part. Or another way is your EB over N naught times this cam stuff is held constant. So anyway, the effect of that, one of the effects of that is that we're actually increasing in total noise power as we go this direction now. The total noise power between the vertical plots is the same, but we increase when we go that direction. But our underlying Gaussian power. And the reason that makes sense to think about it that way is because your Gaussian noise comes from the thermal noise of your receiver, and that's relatively constant for any device. So you're going to know what that is. And oftentimes your non-Gaussian noise, whether it be impulsive or whatever, is going to come from some like external interferer or something. So you should know what your Gaussian noise is, that's constant, and then you can look at scenarios where you just have stuff on top of that. Okay, so if we then take those noise scenarios and throw the QPSK signal onto them and try to detect it, you can see, again, we'll look at the bottom plots first because those are easiest to understand. We'll see that we can find our signal, we can find our signal, we can still probably find our signal. But then here you can't see anything. The reason is because there's just way too much noise. And like I said, we're increasing our total power as we go that direction. So that should be expected. Same story with the second row. Mostly same story with the third row. By the time you get to the fourth and fifth row, the same story happens with the blue one. As we increase our total power, we eventually can't see our signal at all. But the robust estimators can still perfectly see it, totally, very easily, with even across here. And one other thing I'll kind of point out just to reinforce that whole idea of keeping the underlying Gaussian noise constant. You can see that you can see that whenever we can detect our signal best, we always max out at around 9 dB from here to here. You can see that these axes are all from -10 to 0, and you got 9, 9, 9, 9, 9, 9, 9, 9. Because you can't do any better. That underlying Gaussian noise is constant, so you're not going to get better than 9. But you can get 9 for the robust scenarios, you just can't for the non-robust. So let's, again, do the same thing with convert these are 500, using 500 segments, so let's use 10 instead and look at the histograms. And starting again with mod plots because they're easy. We got high effective SNR, which is what we saw. You can see that. High, slightly lower. 0 effective SNR, which makes sense because it was just a flat line in the previous plot. You couldn't see anything. So in the interesting plots, mainly on this second row down, for the traditional method, you mostly get 0 effective SNR. Every once in a while, you might be able to find your signal. But you can contrast that with, for the robust methods, the red and yellow, you're almost always getting a high effective SNR 8, and every once in a while you can't find it. So we've increased our robustness to the impulsive noise, and you can see performance increase here because effective SNR is generally higher again, and sometimes the blue is lower, and here and here. So yeah, kind of the upper left corner is where the increase is. All right, we are almost done. So again, that was with the Welch. Kind of same story with the multi-taper stuff. I said there were 2 other things I wanted to investigate. One was if modulation of the signal changes anything, and one was segment length. So signal, this is easy. Look at, no, it doesn't change anything. And that's expected because this is an energy-based detection method. So if my QPSK signal has just as much energy per sample as my 16-pump signal, which does, then the performance really shouldn't change. And these are the second and third rows extracted. So it would be this scenario with these 2 rows extracted, because those are the interesting rows, right? Like the bottom 2 rows, as we've seen, aren't impulsive enough to make any distinction between the methods. So yeah, you can kind of compare the corresponding plots here, and see that they look pretty much the same. So that was expected. Where it gets a little more interesting is segment length. So by default, I've been showing plots with 256 segment length. And if we reduce that to 64, we get this. So let's see. So here in this scenario on the third row, none of the methods were ever able to detect the signal. They always had 0 effective SNR. If we decrease the segment length, half of the time the robust methods can find it. The robust methods have a high effective SNR. The reason is because it's if you have a shorter segment, it's less likely that your segment will contain impulsive noise. And so it's more likely to be compensate. This is really important to keep in mind because let's say you have some application where you're going to have some impulsive noise you want to deal with, and you know how it's characterized, the characteristics of it. You could fit the Middleton Class A model you could fit it to your noise, and you know, if it's this scenario, you know that if you want to use the robust method, you're going to need a shorter segment length to get any advantage. So anyway. Here are the pictures that I used from Wikimedia Commons. So in conclusion, the Welch method, I can take the extent method and change out the mean for robust estimators and make it a little more robust. The parameter ranges for the Middleton Class A model, in which it's useful, is gamma less than 1, A less than 0.01, but recall that that can be expanded by shortening the segment length as we just saw. So that's just an example for the parameter size. And I didn't talk about this too much, but everything comes out of cost. Engineering is always about trade-offs. So what do you get for this robustness? Well, the first thing you get is computational cost, which actually I don't think that's the biggest drawback. It's not that bad because you're already computing the Welch, or you're already computing a power spectral density estimate. And the increase percentage-wise isn't really that much. So actually I might switch these. It depends on it really depends on the situation. Sometimes your resources are really limited and you're already at the bounds. And sometimes, yeah, you can't afford to have a less optimal estimator. So that's the end. Any questions?
See, if I get it right, you don't incorporate fadings in your simulations.
Fading, no.
Everything is additive noise. What do you think if I incorporate, let's say, radio fading or rational fading in your method?
You know, that's an interesting idea. So I'm not really familiar with fading channels, but that one big difference that would do is it would well, if the fading applies to the noise, would it
Fading you can consider apply to the signals and
just the
noise.
signals in it, or also the noise?
Consider to the signals and the noise will keep the same because noise is in the receiver. But fading is in the
Well, some noises in the receiver,
Yes.
those kind of things. Depends. I'm not really familiar enough with how fading affects energy detection methods to know how it would affect it. It's a good question to look into. I think the only other thought I had that would be similar to the fading is, let's say you have a source that's like an external source that is causing this non-Gaussian noise, and that's going through some sort of fading channel. That would give time correlation to your noise, and the Middleton Class A model has no time correlation. So that's one of the big drawbacks to it, but one of the things that I really wanted to get around to but I didn't get to is there's a generalization of the Class A model that adds a fourth parameter that is a time correlation parameter. And so I thought a little bit about, I haven't done any experience, but I thought a little bit about what if your noise is time correlated, would that help, would that be worse or would it be better? And I think it would actually be better in some ways. All just gut feeling though, so I haven't thought about if the signal's faded.
Did you have a chance to compare the idea you proposed here to some other common detection algorithm like signal stationary convergence detection algorithm?
Yeah, that's a really good question. So I didn't because it was a little, my goal was to take the a method that fit in the subset of, you know, quick energy detection, blind, like all these things, and see if I can make them more robust and compare back to those methods. To compare to like a feature-based method would have, yeah, I'm not even sure exactly how it would have done that. But it's just, yeah, they're kind of in like a different domain of signal detection.
Because some art detection algorithm kind of outperform the energy detection in some low SNR area. So probably you can have some kind of probably some insights like when you do
Yeah.
some kind of comparison between those two algorithms and those algorithms.
Yeah. Yeah. Any other questions?
So let's thank Joe again for the great presentation.
Hey, actually pretty good on time.
40 minutes, right? Yeah, 40 minutes.